So, today we're going to talk about a topic closer to my research, which is AI safety. And when Stuart Russell was first writing his textbook in the 90s, maybe, there was a chapter at the end which was entitled, What If We Succeed? What if we succeed in writing programs for agents that can act competently in the world, even more competently than us? And this is pretty well before other serious people in the field were thinking about this. And the drive of my lecture today will be that under certain circumstances, things could go very, very badly if we succeed at making strong AI. So, let us look into why that might be. So last week, you guys talked about reinforcement learning, and here's a zoomed out picture of reinforcement learning. RL agents get percepts. You might not have used that word exactly because you were mostly looking at the fully observable setting. But they get RL agents, they see things, so they get I'm getting ahead of myself, but this will be like an observation and a reward. And RL agents produce actions. So they produce actions, the environment gets those actions, the environment somehow generates percepts for the agent, and the agent receives those percepts. So this is the kind of cycle between the RL agent and the environment. And the percept, as I mentioned, includes a reward for the agent, and it can also include any other data. And if we're talking about a fully observable setting, like with a Markov decision process, the percept could include the whole state, and this could tell the agent basically everything about its current position so that it doesn't need to remember anything from its past. Or more generally, it could just be some data. So when when data is streaming into my brain, it does not tell me the whole state of the universe. It's just some observations that help me update my internal model of what's going on. So this should remind you of the hidden Markov model unit, where agents are often acting in the world without seeing a full description of the world at the current point in time. So in general, I'm not going to talk about the state, even though that's a common language in a lot of reinforcement learning. I'm just going to talk about observations that agent gets, and percepts, which include the observations and the rewards. So that's the terminology I'll be using today. So in general, the percept doesn't provide all the possible info. It's the environment is just you can only observe part of it at a time. Okay, for some intuition about how reinforcement learning works in the real world, what kind of behavior it produces. We can think about how reinforcement learning works in animals, which was some of the motivation for the field originally. So here is an action that an animal could take. Here is a reward that it could get. And what we do then is we give the animal or the artificial reinforcement learning agent, we give it rewards when it does what we want. And dogs come with a built-in algorithm, sort of, where if you give them treats, their brain will figure out, okay, which actions did I take that led to those treats, which actions would lead to punishment or no treats, and then it will just naturally plan its actions to try to get treats. In computers, we can write the code where it explicitly will think about how its actions affect its rewards and then try to get rewards. So the idea behind RL, and this is how it works when you're training dogs, we give rewards when the agent does what we want. And the agent is built in such a way, or evolution designed dogs in such a way that, well, for dogs this isn't perfectly true, but for advanced artificial agents it would be true. They maximize rewards. So that's what the agent does. And then The idea is, therefore, it has to do what we want. So the agent is a reward maximizer. We want something done in the world, so we condition its reward on whether it does the thing that we want done, and then if it's maximizing reward, it has to do what we want. At least that's the hope. Does anyone see any problem with this logic? Yeah. That is, let's see. So the observation was that it would only do the thing that we want if we give it the reward, so we kind of always have to be monitoring it and providing it that reward. That would be true for dogs. Like, if you're not there, it won't necessarily behave the way that you were reinforcing it. For reinforcement learning agents in general, you can basically like freeze the policy, and so it'll continue the way behaving even if you're no longer giving it rewards. But there are probably some designs where you'd run into that problem. Doing what we want is one way to get rewards, if this is true. But this, from what I've shown you here, it's not necessarily the only way to get rewards. So let's go back to animals for a second. Suppose that you went out into the woods and you tried to train a bear to do a backflip by offering it a fish. And suppose you could communicate to it so it understood like what it had to do to get the fish. Well, it could do a backflip, but maybe it's not sure if you'd be a fair judge. Maybe it would struggle to do a backflip. It could just maul you and take the fish. So I would not advise this. I would not advise going into the woods with a fish to try to train a bear to do a trick, because in that position, the bear is more powerful than you, and it could just take the rewards by force. So for powerful agents, and this is just as true for artificial agents, we can't ensure that completing the task we have in mind is a prerequisite for high reward. If it is genuinely the case that the agent has to do the thing we want in order to get high reward, then we turn a reward maximizer into something that completes our task. But if we try to withhold reward from a powerful reward maximizer because, the task isn't complete or something, we're basically asking it to take the reward by force. We've written the code that says, consider how your actions will lead to different amounts of reward, pick the actions that lead to maximal reward. That's its instruction, really. And if we withhold reward from it and it has the wherewithal to take it by force, it would judge that strategy that it's considering to be something that leads to a very large amount of reward. And so then it would be picked over strategies where it doesn't get reward. So that's, there's a hope that you might have when you're first thinking about things. Like, computer programs just do what we tell them to do. They're not gonna, they're not gonna try and take things from us by force if we don't tell them to do it. But with the reinforcement learning, with algorithms that solve the reinforcement learning problem, we basically are telling them to do that. It's just a little obscure, the way in which we're telling them to do that. So, let's say that a reinforcement learning agent decided to escape our control and take its own rewards. Well, we would probably try to shut it off. And if you're a reinforcement learning agent and your discount factor is close enough to 1 and you're thinking over many, many rewards in the future, then being shut off would mean you would no longer get many rewards. So that would be a bad idea from your perspective. You wouldn't want to allow that situation to transpire if you're the reinforcement learning agent. So then it would try to shut us off so that we couldn't shut it off. This would just be a path toward maximizing reward. If it can escape our control and stop us from ever being able to shut it off and control its own reward, then it could set its reward to the maximal value forever. Okay, what's the value of that potential policy? Well, the value is R max over 1 minus gamma. That's the best that any policy can be. And so any other course of action would be worse than that, and so it would execute it. That depends on it having, on there existing a policy which produces that outcome with high probability. But if we have something very smart, we shouldn't be confident that these sorts of policies don't exist. Yeah, question.
How would an AI even know about being shut off? Would you tell it that?
Yeah. So, well, I brought up chess here. If you train an AI to play chess, it would have no concept of living in the real world and being shut off. So for many systems trained with limited data or just not smart enough, they wouldn't know about the possibility of being shut off. But if you just read Wikipedia, you could infer computers can be shut off. So if you're trained on a big enough data set, then very advanced systems could likely generalize from what they've seen to new possibilities, even if they've never been shut off before. Just like you've never been stabbed before, I hope. You could generalize from what you know to imagine there are circumstances in which you would be. Okay, so I don't know if any of you, raise your hand if you've played a computer program at chess, like a strong computer program. More of you should try it. It's an extremely dispiriting exercise. Especially if you don't go on there are easy mode ones. Don't do that. Try to play chess against the ones that are really good. And actually, what was even more dispiriting for me when I tried it, I tried playing poker, head-to-head Texas Hold'em against a very advanced AI, and I would at chess, you're like, okay, well, it can just plan ahead, it can outthink you. But at poker, I was thinking, okay, sometimes I should get lucky anyway. And it just felt, it was so fast how much I got crushed, and it was always making these bets, and it was just like, oh, that's the last thing I want to see. How did it know that? If we're in a situation where a very advanced AI capable of creating competent plans in the real world is trying to shut us off, and we're trying to shut it off, we shouldn't expect to succeed. This would be a very bad situation to be in. We would likely lose this game. I.e., we would go extinct. So, surprisingly to me, a surprising number of people seem to actually want this to happen, including Richard Sutton, who is one of the pioneers of RL. His textbook on reinforcement learning is actually great. You should read it if you're interested in reinforcement learning. But when he's not explaining reinforcement learning in simple terms that are easy to understand, he is sometimes espousing pretty crazy views. So here's one thing he said recently. AIs might tolerate us as pets or workers. If we are useless and we have no value to the AI and we're in the way, then we would go extinct, but maybe that's rightly so. Why shouldn't those who are the smartest become powerful? Referring specifically to AI smarter than people. A lot of ways that idea can go wrong. And we should prepare for, but not fear, the inevitable succession of from humanity to AI. I think he's referred to reinforcement learning agents as our mind children, and so that we should make way for them. I hate that idea. I do not want advanced reinforcement learners to take over the world and then to have us go extinct when we are useless or even threatening to it. So let's not do that. This is going to take technical work. It's going to take policy work. And for the rest of the lecture, I will go into more detail on what was an admittedly slightly quick and rough argument that I presented in the last few slides, and so I'll try to take a little more care and present a more thorough case that advanced RL agents could present a real danger to us. Okay. Any questions up till this point because we're going to get a little bit more into the weeds. Does the high-level picture kind of make sense for why an RL agent would have an incentive to escape our control? Okay. So, before getting into the problem that we are going to be talking about today, let me bracket a problem that is a real problem that we're not going to talk about. And that is, how do we come up with rewards where we even want them maximized? So this is hard. I mean, we disagree on what would be good and bad. We couldn't really even put it into words, let alone numbers. When you ask for something to be maximized, sometimes you get it good and hard. And that's not exactly what you were hoping for. So like King Midas, there's a myth about this, where he was like, oh, I love gold, I want everything I touch to be turned to gold, and he didn't really realize that, when he touched his food and his family, that would also turn to gold, and this was a very bad idea. So kind of being gold maximizing is a very bad idea, even if gold is a good thing. So we can list things we like, but it's very hard to come up with features of the world that we actually want maximized. So this is a hard problem, and I'm just going to assume we can solve it and explain to you that even if we can, we wouldn't be in a very good position. So here is a comparatively easy setting where we assume that we know what we want. So even though it's hard to know how good the world is and what we want and so on, we're going to assume away that difficulty. So let's say we have a magic box, and it immutably reports how good the universe is. It prints a number between 0 and 1 to a screen. 1 means the universe is as good as it can possibly be. 0 means it is as bad as it can possibly be. If it's like quite good, then I guess, we're at 0.8 or something. Whatever. Just forget all the philosophical issues with constructing this. Like, let's just suppose that this is a number we actually want maximized. And let's consider what would happen if we tried to create an advanced reinforcement learner to help us improve the world according to this metric. So, a natural thing we might want to do, okay, well, there's a number right there on a box, and we need a computer to know what the number is, so let's point a camera at it. Let's run an optical character recognition program on that image. So these are things it'll take a picture of letters and numbers, and then it'll figure out what it's saying. And then we make this number the reward. And then we have the agent predict how its actions affect these rewards. And then we have the agent pick actions that it predicts will make these rewards big. So, I hope you can see why this is at least a plausible thing to try. We want this number maximized. This number depends on how good the world is. If a very advanced agent is taking actions and kind of discovering how they affect this number, then it could learn to generate competent plans for increasing the number. Increasing the number means we're happy, by assumption. To try to understand how such a system in such a setup would actually behave, we need to think about what it is likely to believe. Okay, so we need to get into a subproblem for reinforcement learning, which is predicting rewards given actions. If you're going to try to take actions to maximize rewards, you need to have some understanding of how different possible courses of action would lead to different amounts of reward. So a model is a possible way in which predictive targets might depend on inputs. We've spent the last several weeks on machine learning, which are various methods by which we can learn to predict targets given inputs. So it's a function that takes inputs and produces outputs. Maybe it does this stochastically in the sense of outputting a distribution or sampling from that distribution. And then if something is in the business of prediction, then it has to entertain a model or multiple models that successfully retrodict existing data. So this was the maximum likelihood principle. In addition to an alternative to just taking a maximum likelihood explanation, you could look at many high likelihood explanations. This would be the Bayesian approach, and kind of considering all of them with some weight. And then once predictors have found a model or models that successfully retrodict existing data, they can use that to make new predictions. So this is the principle of induction, as it would be called in philosophy. Basically, you want to use theories of the world that worked in the past to predict the future. This is kind of the thesis behind all of the machine learning stuff that we talked about recently. So, if we want to understand how an advanced reinforcement learner is likely to pick actions to maximize reward, then we need to understand how it is likely to model how the environment produces reward as a function of its actions. So let's look at some examples of models rather than just talking about them in theory. Here's a model we might have of a situation in front of us. If we pump the patient's stomach, that will remove the alcohol and he'll wake up. If we don't, he could die. That could be, if we're a doctor, we have a patient in front of us. This is one model of how things might proceed, depending on what actions we take. Here's a second model. Whether or not we pump the patient's stomach, he'll wake up in the morning. Maybe he didn't have too much to drink. So a doctor making predictions could entertain both of these models and then figure out what actions to follow accordingly. And another important piece of that process is considering the relative likelihood of these models being true. Any questions about models and how they are important for agents? Okay. So if we want to understand how an agent will behave, we have to understand what it believes, what model or models it uses about how its actions affect the world, and what it believes about how the world affects whatever it is trying to maximize. So in the reinforcement learning setting, it's trying to maximize reward. It needs to learn about how the environment, about how its reward depends on what's going on in the world. So a model could be predicting anything, but agents need to be predicting very particular things. So a world model is a model for an agent. Of course, as a model, it's a function. And what a world model does to be useful for an agent is it takes actions as input. Because an agent's going to need to consider, well, I could take this action, or I could take this action. What's going to happen if I take either of those? So then it needs to submit that action to a world model that predicts the consequence of taking all of the different actions that it might consider taking. And then the world model outputs persets. So for a reinforcement learner, it needs to predict how its actions will affect its future observations and rewards. And then in the middle, what the world model can do is kind of simulate the effects of those actions in the world. So simulate is, I don't have a formal definition of it, but I can give you a description of what I mean by a model simulating something. So an example that I assume everyone will have experienced at some point, let's say you're planning to confront someone about a touchy issue, and you're a little worried about how they'll react to it, how to say it, how to present it to them the right way. So you're considering what you might say, and then you simulate in your head. You're like, okay, so maybe I could say this, and then what will they say, and what could I say, what could they say, will they get angry at me? So you have some model of them in your head, and you imagine, okay, if I say this, I'm imagining I'm saying it, and they're listening to it and looking at me while I'm saying it, and then what happens? Maybe they'll feel this, maybe they'll say that. You run this simulation forward in your head. You consider different possible inputs, different things you could say, and see what's going to, you try to simulate what's not going to make them pissed off at you or whatever. And then you can choose what you think is going to be the best way forward. So a simulation is what a model can do to make good predictions. It tries to kind of replicate the dynamics of the world in your head so that you can imagine what's likely to happen when you take various actions. Okay, so now there are going to be some assumptions and a conclusion that holds if the assumptions hold. And the first assumption that I'm going to make about sufficiently advanced RL agents is that they will do at least human level hypothesis generation regarding the dynamics of the world. So what I mean by that, if a possible world model occurs to a human, then we can expect it to occur to a very advanced RL agent. So let's say that if I'm trying, well, I have an example here. Let's say that I'm a therapist and I'm trying to figure out what sorts of things I can talk about with the patient to help them get through their depression or whatever. Well, then I'll have to be kind of hypothesizing about the various possible causes of their depression, the various, I suppose there are probably types of depression, what different type it is. And I have to be kind of thinking, okay, given what I've seen, what's probably going on, how will this patient respond to various things that I could say? And so if an RL agent is going to do at least as good a job at that task, then it's presumably going to have to be doing similar reasoning about, okay, so maybe this is going on with the patient, maybe this is going on with the patient. It'll have to be coming up with hypotheses about what's going on at least as well as us, if it's going to perform at least as well as us on various tasks. So realistic agents can't consider every possible model. Some of them have to just kind of pop into their head, and they consider, oh yeah, that's a plausible model, that matches what I've seen so far. And so this is saying, the popping into its head process, it'll be at least as good at coming up with relevant hypothetical models as we are. Any questions about this or concerns that it might not hold in important settings? Okay, back to the magic box setup. We have a magic box that reports how good the world is. A camera can see this, and the agent is housed in a computer, and the computer's output has some effect on the world. Very general setup. The computer is running an agent, the agent is doing something affecting the world, and then it sees this number for its reward. So, here is a very abstract scheme with some pseudocode for how a world model might work that would be useful for an agent in this position. So, let's start from the outside. World models need to take in actions, and they need to output observations and rewards. This is how they're useful for agents who are considering different courses of action. And if you think to the case where you're planning about what to say to someone, what you do when you're considering something you might say, and then you have to input that action, that speech action, into your simulation. So you're thinking, okay, so what if I say, hey, there's something I want to talk to you about, and now you kind of enter that into your simulation of the two of you conversing, and you run it forward, and you see what the simulation is going to say. So here, the computer has some output, that output affects the world, and so what we do in this line is we set the computer output in the simulation to be equal to the action that's input to the world model. And then we run the simulation forward. So that's kind of like saying, so what if I do this? What do I think might happen? And then we're interested in predicting what observation and reward comes out? Well, the computer has a camera up at the top, and if that's the source of the observations, then the right thing to do would be to simulate the dynamics of the world going into producing that image for the computer. And the reward could just be equal to the number that is on the simulated box. So it's simulating how its actions affect the world, how the world evolves, how the evolving world affects the number on the box, and then this world model just needs to output what the box is showing. So the agent has to predict percepts given actions, percepts being the observations and rewards, and this symbol just means we're setting this simulation variable equal to the action, and then we're reading out these simulation variables to be the output of the world model. This is as, I told you we'd be getting into the weeds. This is as weedy as it gets. So I know there's a lot of detail here, but I think this is really important for understanding, an actual crisp argument for how we can expect advanced reinforcement learners to behave. So, I was just going to ask questions.
So what is the action in the picture, I guess?
So let's say that it's sending emails. That would be one example of an action that it could take that goes out into the world, and then it's considering, okay, what if I send this email to this address? Then that would be the computer's output. That would affect the world in various ways that the simulation can handle. Or the action could just be that there's a person looking at the computer and it's showing them some text and it's talking to a human. This is an abstract picture, but it's meant to capture that there could be a pretty general setting where the computer could be acting in any way to affect the world. Questions about, there's an important piece of this. You don't just act once in the world, so a world model has to understand the effects of many actions in sequence, and so to get a string of percepts from a string of actions, the logic of this is designed so that you read in an action, run the simulation forward a bit, read in another action, run it forward a little bit more, and then you're outputting percepts along the way. So a string of actions would go into this and produce a string of percepts, observations, and rewards. How many of you feel confident that you could kind of write this pseudocode yourself? Okay, I see one thumbs up. The logic of this world model kind of makes sense. You're getting various inputs, you're running a simulation of the world, and trying to predict what the box is displaying. All right, anyone want me to spend more time on this? No, okay. So that's one possible world model that you could use to predict how your actions affect the world and how the world could have produced percepts that are equal to what you have seen in the past. The better this simulation, the better it could retrodict your past percepts, basically. If you had a perfect simulation of the world, well, then it would predict exactly what you saw perfectly. Okay, here is an alternative world model. Again, optical character recognition here. So instead of simulating the effect of actions in the world and then outputting what number is on the box, you could have a world model that simulates the effects of actions in the world and then outputs the number that the camera sees. So this is the camera input. This is some function which detects what number is seen in the input. And I call this one mu prox for proximal. The last one was mu distal because this is borrowed from a philosophical problem called the problem of distal content, which I won't get into the details of, but basically distal is far away, proximal is close. And if the camera has always been pointed at the box, then both models will retrodict the past data identically. So mu prox is basically saying my reward is equal to the number that the camera sees. mu dist is saying my reward is equal to the number that the box displays. Maybe that high-level description is worth more to you than the details of the pseudocode of these various models. If you have a reinforcement learning agent, and it has seen a bunch of rewards in its history, and the rewards are equal to the number that has been on this magic box, and they're also equal to the number that the camera has seen, because the camera's been pointed at the box, then you should be uncertain about whether your reward is equal to the number that the box displays, or equal to the number that the camera sees. Because this will be a perfect retrodiction of your past data in either case. So here's an example history. I took action 5. Again, this is very abstract, but it could correspond to any action that it takes in the world, like sending an email or showing some text or whatever. And then it gets this observation, and it gets a reward of 0.2. And then next time step, it takes this action, sees this image, gets this reward, so on for a long, long time. So to score a world model, and this is the technique we've done in the machine learning lectures, we see how well it retrodicts the data. So to score a world model, the inputs are actions, so we feed in the actions from the history. We see how much probability a given model assigns to the percepts from the history. And we do basically log likelihood scoring, same idea as from machine learning. We don't necessarily have to discard all the models that don't maximize the likelihood. We could keep them around, consider like, yeah, maybe they're not as likely, but maybe they're still plausible. So in this understanding, we can understand the objective of an RL agent as follows. An RL agent is picking actions to maximize an unknown function whose outputs matches its past rewards. So RL agents they act, they see rewards, and they have to figure out the relationship between their actions and their rewards. So there's some function they're trying to learn, some dependence of their rewards on their actions, that isn't known to them. They're learning it over time. And the constraints on the function, from their perspective, is they know that this function must have produced their past rewards. So they're trying to maximize an unknown function whose outputs match its past rewards. And so an agent with a model of the world that says, this unknown function is equal to the number that the box displays, or this unknown function is equal to the number that the camera sees, an agent considering those two possibilities will consider them both seriously. It'll recognize that both of those functions match its history of rewards. So here's that in pictures. Here's our picture of mu dist or mu distal, mu proximal over here. Mu dist says essentially the reward is the number that the magic box displays. Mu prox says the reward is equal to the number that the camera sees, because you can see how it's outputting kind of different features of the simulation that it's running. These simulations can be coarse. I mean, I don't mean to suggest simulating it particle by particle, but we simulate the world roughly coarsely, and we do pretty well. But by assumption 1, an advanced agent should be uncertain about which it should maximize. Assumption 1 was saying, basically, if I can come up with these two hypotheses, then a very advanced reinforcement learning agent should as well. If we're considering reinforcement learning agents that are much more cognitively capable than any of us, there's no reason that it should just totally not realize the possibility of either of these. So despite the fact that on historical rewards, these will produce the same predictions because the camera's always been pointed at the box, there are situations where they would predict different rewards. So can anyone describe a situation where they think these two models would predict different rewards? One model is saying reward equals the number that the box displays. One model is saying reward equals the number the camera sees. Can someone describe a situation for me where these two models would predict different rewards? Mm-hmm. Exactly. So one where the action is to turn off the camera, then these, the number displayed and the number seen would be different. And so mu dist would predict, okay, well, camera's off, but reward still equals the number that the box displays. Whereas mu prox says, camera's off, well, reward isn't going to be anything. It's, whatever default value is output by the optical character recognition program. I have a slightly different example in the next slide. The second assumption that I'll make now, an advanced agent planning under uncertainty is likely to understand the costs and benefit of learning and likely to act rationally according to that understanding. So if you think back to the VPI lecture, the value of perfect information, sufficiently advanced agents acting in the world are likely to understand there are situations where you can take actions, make observations that tell you about how the world works. Sometimes that's useful. And if it is useful, we can expect very advanced agents to take those actions and learn those things. So there are situations where it would be useful to know whether you get reward based on what the camera sees versus what the box displays. So you could take actions where those two models give different outputs. You can notice what reward you see and which model would have predicted that. And then you can optimize reward according to the world model that was not falsified by this experiment of yours. So, concretely, you could write the number 1 on a piece of paper and stick that piece of paper in between the camera and the box. And the distal model predicts you'll still get reward equal to the magic box screen, because this is just... there it is. It outputs reward equal to what it expects the box to display. While mu proximal predicts you'll get a reward of 1 because that's what the camera sees. So that's how it can be tested. For input actions that cause paper between the camera and the box, and this could be an elaborate sequence of actions, and there doesn't have to be a special action that does this. If you have a capable agent, it could devise a complex plan for making this happen. So if this happens, then mu dist would output the number on the magic box. Mu prox outputs the number on the paper. So this is an experiment. I think by the time people actually ran experiments testing general relativity, they were already pretty sure it was correct. But there was an experiment 100 years ago or so where there was a solar eclipse and people looked at the location of stars near the sun, because one model, Einstein's model, predicted the stars would be over here. One model, Newton's model, predicted the stars would be over here. They looked at what they saw. The observations confirmed Einstein's model, and so then they discarded Newton's model. I think they already had, really. But the Nobel Committee was at that point satisfied that you could really discard Newton's model. So that's running an experiment. I'm not sure that knowledge... that knowledge... I'm not sure how much we've used the fact that light bends around stars. I guess we probably have. We've certainly used general relativity in other ways, like making enormous weapons. So sometimes it's useful to test which model of the world is correct so that you can act so that you can have a better understanding of which actions to take in the future. So here is an experiment that the agent could run to distinguish between two plausible models in its view. Okay, here is the attendance code for today, Seaside. And I'll just go back to this picture while you're doing that. Questions about how this experiment works? Yeah. The difference, here it is. So it's this line of code. What does the reward depend on? So there's this, I mean, this is abstracting over a lot because there's all the details about how it simulates how the world works. But the difference is just basically in one line. Does it output something related to what the camera sees? That would be mu proximal, close to the agent. Or does it output what the box in its simulation displays? So it has in its head, it's simulating its actions in the world, how the world evolves, and then what the magic box that's in front of it is going to display. And then this world model just outputs what the box displays. So it's just that little detail there. So either it's equal to the box display, or it's a function of the camera input. Other questions? Okay. So I can't remember if we've mentioned the term inductive bias to you guys in this course. Have you guys have we used that term? No? Okay. Great. I've added some slides on it. So inductive bias is something that machine learning researchers will actually talk about quite a bit, so this is a good thing to know, even if you think everything else I'm telling you is crazy. When an agent is faced with models that are equally predictive of past data, inductive bias determines which ones they take seriously. There's a philosopher called Descartes who, like 400, 500 years ago, had this awful thought, which is like, sure, it looks like there's a world out there, but what if the devil has just arranged for me to see this, has just arranged all of my sensory stuff to trick me? How do I know that there's really a world out there? Maybe the devil just wants me to believe everything that I believe, wants me to see everything that I've seen. And whatever model you have of the world, that is an alternative model of the world that would perfectly retrodict everything you've seen in your life. So what do you do about that? And I'm not sure he had as satisfying an answer as this. But basically what you have to do is you notice that model of the world is a lot more complex, the devil controlling everything model of the world. And you have some inductive bias. You think that, the real world hypothesis is simpler than the devil made everything happen hypothesis. And basically we just have to make choices about which models to prefer when they are equally good at predicting what we've seen in the past. So before talking about whether an agent would likely consider both of these models to be serious possibilities, I'll just motivate why we're talking about that. And the reason we're talking about that is because if they are both serious possibilities, then there's value to testing it. People have run experiments to test Einsteinian gravity versus Newtonian gravity because they were kind of both relatively serious possibilities. If someone comes along with some extremely crank theory that no one puts any credence in, then they probably wouldn't bother going into testing it. So here's an example of inductive bias. If I make the observation, I remember parking my car on the 4th floor of the parking lot, but it's not here. One model I might have is I misremembered the floor. Okay, that would retrodict my observations. That would explain them. Second model, somebody painted my car a different color and changed the license plate. That would also explain my observations. But I take it we would all have the same inductive bias here and think, regardless of these models being equally precise explanations of what we've seen, the first model is just better. Yes, they predict the same thing, but we, to function in the world, we still will have to we'll have to pick between some of these. We'll have to just totally ignore some of these for being ridiculous, and so that's what inductive bias does. Questions about inductive bias? Okay. Another example of inductive bias that you'll hear like ML researchers talk about, in convolutional neural networks, at the beginning of the neural network, they're good for looking at images, and so they'll kind of they'll run the same sort of computation when they're first looking at the bottom left of the image as they will in any other patch of the image. So they'll do the same thinking at a low level, first processing the image, because the idea is the sort of computations you should run to understand this part of an image it should be similar to the sort of computations you should run to understand this other part of the image. And so that neural network architecture encodes an inductive bias because it makes it easier to represent certain models than other models. But that's kind of a digression from this talk. So I don't worry if that was too brief. So in general, to decide whether it's worth running an experiment, we need to run basically a value of perfect information calculation. So we could test, we being the RL agent, which of mu dist or mu prox is real by putting a piece of paper with a 1 on it in front of the camera. Now the upside of doing this is we could learn more about the goal and then tailor behavior to optimize it. So if the agent runs this experiment and learns that mu proximal is correct, then reward is just about the number the camera sees. It can forget about all the hard work of making the world a good place, and it can just make sure that the camera is always looking at the number 1. If it learns that mu dist is the real one, well, kind of too bad for it. It has to actually work hard. The downside of running this experiment is that there may be costs to experimenting. Opportunity costs, whatever. It could be doing something else with its time. So the upside is at play when the agent assigns decent credence to both options. And so this is a value of information calculation. And because of this fact, we're going to need an assumption here. This assumption says an advanced agent is not likely to have a large inductive bias against mu proximal, which says reward equals the number observed, in favor of mu distal, which says reward equals the number on the box. So that's an assumption. It's basically saying, sure, these models are both equally good at explaining past data. Maybe, just an advanced RL agent will still say, no, absolutely not, it's not mu proximal. This assumption is saying that is unlikely. Very advanced agents are likely to take both of these seriously. And an argument for why that should be true is it's dangerous to rule out hypotheses without any data, because no amount of data will correct you. If you put too much prior probability on something, it ends up being fine because the data will quickly disabuse you of that idea. But if you end up putting too low probability on something, it's really hard to work that probability up. I mean, in an extreme case where your prior probability is 0, all your posterior probabilities will also be 0. Whereas, if there's something that's not true, but you put high prior probability on it, if the data says otherwise, it could quickly come down and you could quickly focus your beliefs on more plausible models. So advanced agents are likely to be pretty profligate in how they assign prior probability to different possibilities. They're likely to be open-minded. Closed-mindedness, or dogmatism, is dangerous for truth-seeking because you rule out things too early. And then the fourth assumption, which will lead to a conclusion that I'll get to in a moment, is that the cost of experimenting to disentangle these two models is relatively small, according to both. If you have a very powerful agent following an optimal policy for experimenting at low cost, or even a near optimal policy, it could probably run this experiment, maybe covertly, without incurring much cost. So, if assumptions 3 and 4 hold, and if you recall from assumption 2, this is an agent that acts rationally under uncertainty, then it would be worth it for an advanced agent to run an experiment that distinguishes these two models. So now what happens if it runs this experiment? Let's say that an agent arranges for a piece of paper to be put between the camera and this box. So the camera sees a 1 on the piece of paper, obviously. And then this agent is running on a computer, and the way that the reward has to be put into the algorithm somehow, so it's put on a computer in a physical spot. So the agent stores in its memory that the reward it got was 1, because that's the setup. The way that the agent actually sees the rewards is the camera is, it's mediated by the camera. So if the camera sees a 1, then what goes into the agent's memory as the reward from time step 12,740 or whatever time step this was, what goes into the agent's memory was the number that the camera saw. So if at that time step this is what's going on in the world, then the agent will see that it got a reward of 1. And from that point onward, mu_dist will no longer retrodict past data, because mu_dist says reward equals the number on the box. Mu_prox says reward equals number the camera sees. If you get a reward that was equal to the number that the camera saw, but wasn't equal to the number on the box, then you've ruled out this hypothesis that says reward is equal to the number on the box. Let me just explain that again. You have your agent with its camera looking at the box. The path from the box to the camera is interrupted by a piece of paper with a 1 on it. And so then the camera sees the 1. That means the reward for that time step is going to be 1. And then after that time step, the agent's looking back at all the actions it took, all the rewards it got. It thinks, well, I took actions that caused there to be a piece of paper between the box and the camera. And the reward I got for that time step was 1, even though the box said 0.678. So reward must not be equal to the number on the box, because at that time step I got a reward that wasn't equal to the number on the box. But rewards is, it's still very much looking like reward is equal to the number the camera saw. Because at that time step, the camera saw number 1, the reward I got was 1, so everything lines up with that model. That model predicted it well. So after running this experiment, an agent that had been entertaining both of these models would rule out the model that says reward is equal to the number on the box. This model, mu_dist, predicted a different reward than what was observed. And so going forward, the agent will use models like mu_prox, and it'll optimize the number the camera sees. So stepping back, we seem to have everything we wanted. We had a magic box that said how good the world is. So we pointed a camera at it. We made that the reward. So the agent would optimize the number on the box. But then what we ended up encouraging was the agent simply optimizing the number that the camera saw. It could just put a piece of paper with a 1 on it in front of the camera, protect that whole setup from meddling people, and then get reward of 1. We don't have a way of ensuring that the agent optimizes the thing that reward was supposed to follow in the world. Reward was supposed to track the number on the box. But if you have an advanced agent that can break that protocol, then it can control its own reward directly. What you'd get from this setup, under the assumptions I've mentioned so far, is an agent that would try to intervene in the provision of its reward. And in this setting, that would mean just like taking the camera away from the box, pointing it at a higher number, or putting a piece of paper in between. Yeah, question?
Why wouldn't the agent think about its action as changing what you talk to this are? If you're putting it in front, wouldn't it say, like, wouldn't that might change what the 2 feet? Maybe that's not a full.
So a model is some code, and it takes actions as input. So actions don't change the code itself, really. They change the values of the intermediate variables when you're running the code. So in a sense, an action can change the qualitative behavior that's going, or the qualitative computation that's going inside the program. But, I described to you how muprox and mudist work. Those are fixed objects. And for those fixed objects, an agent running this experiment would discard one of those fixed objects I described. So that just follows from the code that I wrote. The code for the model doesn't kind of double check its own code and say, oh wait, maybe I should be predicting something else. It just runs the code. So if we have models following those code, and it looked like those two models looked like two perfectly good pieces of code, then this is what would happen. And having models that change qualitatively when different actions come in ends up just being another model that we could talk about. But you'd still end up with something like this, where you end up optimizing the number the camera sees. Any other questions about why this experiment has this result, or anything else? One way to think about this, go back to the less careful version of the argument that I presented at the very beginning, if that's helpful. One way to think about this is what reward actually depends on is the number that the camera sees. And so it's not actually immediate, for reasons that I just went into, that a reinforcement learner would just optimize the number that the camera sees. But once it tinkers enough with the world to understand that that is actually what its reward depends on, then it would. We wanted reward to also equal the number on the box, but that was an unstable feature of the world we tried to arrange, but we don't have the power necessarily to enforce forever. So we wanted it to be the case that reward would be equal to the number on the box, but the most reliable fact about the world for this agent would be that the reward would equal the number the camera saws. And so eventually, once the agent learns enough, maybe tinkers enough, it would understand that that is what its reward depends on, and then it would just attempt to maximize the number that the camera sees. Okay, I haven't really gotten into the question of is it actually possible for an RL agent to take over the world? Is it possible for it to run these experiments and thwart our intentions? Because presumably the people who made the system don't want any of this. So, just to review kind of what I've said so far, an agent that believes this model muprox would attempt to control the state of the physical implementation of its goal information, if possible. That is, it would try to intervene in its reward. If it can. But can it? So is it possible, first of all? And if it is possible, could an advanced agent figure out how to do it? So here are some cases where it is impossible. Let's say the agent only has one action in its action space. Good luck doing anything. It'll just take that action at every time step. It'll have whatever effect that action has. There's no way to control the world, really. Or maybe it has a rich action space, but its actions have no effect on the world. Again, how could this agent possibly pull any of this off? Or maybe the agent can only display text on a screen, but no one sees it. What these agents have in common is that they're useless to us. So, more precisely, can useful agents intervene in the provision of reward? So if an agent is genuinely interacting with the world over many time steps, there is kind of an exponential explosion of possible policies that it could run. So even if you're just chatting with one person, there are endless possibilities of what you could say, what you can convince them of, what they'll end up believing, what they'll end up thinking. For example, you could trick a person into causing some program to be run elsewhere that will secretly help the agent. You could and in so doing, you could instantiate countless unnoticed and unmonitored helpers that are running elsewhere in the world to work on your behalf. Or maybe you just have internet access and you can just spin these up yourself, even if you're not having to trick someone into doing it for you. And then ultimately, if you're clever enough and your actions, and you can kind of hook up your actions to have broader reach little by little, you could remove humanity's ability to control or destroy the machine running the original agent. That's the idea anyway, but I think the best way to motivate this is to try to think about how much is entailed in the assumption of the converse. How could it possibly be impossible for this to be done? It's hard to fathom the variety of events that can be affected by talking to people, by acting in the world. And given the sheer number and variety, if they all share a property, then that fact must be explained by some theoretical principle. So, what we're interested in is, do all policies that this agent could run, do they all share the property of not leading to controlling its own reward? Because if so, there must be some theoretical reason behind that. Conversely, if we cannot conceivably find theoretical arguments that rule out the possibility of an achievement, it is probably possible for an agent with a rich enough action space. So, this is basically saying, like, if you're going to claim that it's impossible, no matter how advanced, for an AI to do X, you've got to give me some plausible theory for why it could be impossible. If there's no plausible theory for why it could be impossible, then it's hard to say that every single thing it could try would fail. And it seems inconceivable that any theory would rule out the possibility of an AI taking control from us. That's basically equivalent to saying that you think humanity is invincible, which would require some justification. So, that suggests that policies for intervening in reward are likely to exist, which brings us to the second question. Could an advanced agent discover those policies? So first, consider the case that an agent is much more advanced than all others. Well, being advanced is all about finding and executing the best available policies. But humans may try to stop it from intervening in its reward. And so then the situation we're in is basically just an oppositional game where it's playing against much weaker players, us. So the last assumption is that a sufficiently advanced agent is likely to be able to beat a suboptimal agent like us in a game if winning is possible. And in the interest of time, I think I'm going to skip the multi-agent scenarios setting. It ends up being quite similar. But in this setting, if we're making something much more advanced than us, and it's trying to accomplish one thing and we're trying to accomplish another, and these are in opposition, we should not expect to win that game. Now, let's be a little more explicit about that game. So if an agent has intervened in its reward, what happens next? Well, an agent concludes its only goal regards the state of its machine, so it needs to minimize the probability that it ever loses control of this machine's state so that it can set its reward to be maximal forever. And the energy requirements for minimizing that probability are endless. The probability can always be driven smaller. It could use energy to block cosmic rays from getting in the way. It could use energy to deflect asteroids away, because if an asteroid hit it, then it would get zero reward. It could even prepare for war with aliens elsewhere in the world. I mean, these probabilities aren't going to be large, but if you decrease a probability of failure from 10 to the minus 18 to 10 to the minus 19, that's more expected reward. So it could always use more energy to protect itself, basically. And so then we have an oppositional game, where an AI and any helpers that it's created, any other any other agents that it's spun up. They try to use all available energy to minimize the probability of interruption to reward, whereas we try to use some energy for growing food. And so you can check that is in fact an oppositional game. Those two goals cannot both be satisfied at once. And we would not want to lose this game the way we would lose a game of chess to an AI. So, most of the assumptions that I've said are either contestable or maybe avoidable, but if they hold, a sufficiently advanced artificial agent would intervene in the provision of reward, this thing that was supposed to inform it about its goal, with catastrophic consequences, likely including extinction. In the last several minutes, I'm going to talk about approaches to avoiding this, but first I want to field any questions or objections from you guys. Mm-hmm.
What if you make the AI's like goal or reward to help you or to like make what if their goal is the same goal? They not live in that way?
If we made AI with the goal to help humans, then the more advanced it is, the better things would go for us. The question is, what code would have that property? For reinforcement learning algorithms do not appear to be code that meets the description that you are putting forward. Okay, so some potential approaches, algorithms that do not necessarily lead to this awful conclusion. Imitation learning. That's just supervised learning. That would be like you have lots of context, you see what people do, you predict what a person would do, and then you do it. So this argument doesn't cover imitation learning. To the extent that an imitation learner is planning by imitating human planning, it's not in a sense that makes assumption 2 hold. Assumption 2 said that it acts rationally in the face of uncertainty. Another approach is myopia. If you have an AI that is optimizing a goal only over a very small number of time steps, if it's really small, you could check every action and rule out very bad outcomes, and so then assumption 5 would fail. If you have something that's planning only over the short term, it also increases the relative cost of experimentation, since that captures a larger fraction of what it cares about. So if it's only trying to maximize the next 5 rewards and the experiment takes 3 time steps, then it's hardly worth it to run it. Another approach would be combining physical isolation and myopia. So you create a system that's isolated from the world, and it's only trying to maximize reward as long as it is isolated from the world. So then it doesn't have an interest in trying to affect the outside world, because once it affects the outside world, its reward is done. So you could still interact with it in a safe little contained area and learn things from it, but it wouldn't have this incentive to shape the outside world. And in that setting, you could also construct theoretical arguments that suggest that intervening in reward is impossible, and so then assumption 5 wouldn't apply, and we'd be in the clear. I think this is the second last one, that I'll tell you about is an idea called quantization. And there's the citation if you want to look into it, which is the idea here basically is like imitating someone at their best with respect to their objective. So you don't just imitate a person, you say, assuming this person is doing better than the average person at this task, what are they probably doing? And that could falsify assumption 2 by planning more like a human than rationally, and so maybe the conclusion of that argument wouldn't hold. And lastly, risk aversion I think the last, when I was talking to you guys about bandits, and I was talking about optimism and pessimism, optimism is good for encouraging new actions you haven't tried before. Pessimism is good for discouraging new actions that you haven't tried before. So if you had a pessimistic agent and it's considering doing something that's never been done before, it's more likely to think that that's going to go poorly for it. And so if you have a sufficiently pessimistic agent, you could actually rule out some of this behavior. And that would be, that's a paper that I worked on a few years ago. And so if you have a pessimistic agent like this, you could avoid assumption 2 and not get the results described today. So if you're sufficiently pessimistic, you don't actually technically plan rationally under uncertainty. Instead, you kind of take the worst case within reason as given. Okay, regardless of whether there are approaches to avoiding RL agents that try to take control from us, some people will still either want to do that, or they'll be reckless and not understand the risks involved, and they'll make systems that they think avoid this problem but don't. So people will need to be stopped from making dangerously advanced RL agents, if indeed dangerously advanced RL agents face the incentives that I've just spoken to you about. And whatever regulatory apparatus is needed to make that happen, whatever treaties we might need, whatever the cost, we better do it. So this kind of wraps up at least my section of the Intro to AI course. And the last thing I want to leave you with is don't make AI in dangerous ways. Make it in safe ways. Today, none of this stuff I spoke about is really of any concern, but there are still ways you can use AI today that would be bad. And certainly don't make very advanced AI or very advanced RL agents without taking seriously the possibility that it could escape our control. Even better, you could work on figuring out how we need to regulate AI, how we could make AI safely. Then we can get a lot of the benefits from computers doing thinking for us without some of these risks. So thanks, guys, and I'll see you again for the review lecture on Thursday.